Okay, so let's continue for the electric flux. Okay, so in the last lecture, we just introduced a simple concept about the electric flux. So here we need to have some formulas. We need to have some mathematics to really talk about this in deep. Okay, so first it introduced the area vector. Okay, area vector. So a area vector dA, okay, for an area element on a surface, okay, so you try to define this whole thing, okay, an area element on a surface, okay, maybe you have a large surface, but yeah, actually we need to separate into many more segments, so therefore, many small element, okay, for each element you can consider this is a plane. 就是你可以有一个很大的面很大的面，在这里定义这个 area vector 的时候，不一定是封闭封闭跟不封闭都可以用那你有一个面有一个很大的面，那个面不一定是平的它不一定是一个平面，可能是曲的，但是我们把它切得很小的时候，那每一个小块我就可以把它看成是一个平面 ，OK？ An area element not necessary to be a plane, okay? But even though it is a curvature surface, as long as you separate into many small elements, as it is small enough, then we can consider each element is a small plane, okay? And is okay. So the area vector of this element is a vector. Of course, an area vector is a vector that is perpendicular to the element and has magnitude equal to the area dA of the element. Okay, so it try to define it in two ways. One is the magnitude, another one is the direction. So the direction is perpendicular to the element. Okay, 就是垂直那个小平面。Okay, and then has a magnitude equal to the area. Okay, 所以面积像那样嘛，所以它的大小就等于那个面积然后方向的话是垂直那个 element Okay, so yeah. So of course, if you talk about perpendicular to this element, it can be two direction. Okay, so for some of the case, if you just consider an open surface, 一个开放的平面的话，那两个方向都可以。So both of the direction will be okay. But for the closed surface or when you consider Gaussian surface, then you need to consider the direction. Okay, and I will talk about it one or two pages later. Okay, so in this case, okay, so suppose we have this element. So that we can assume this is a plane, and then we can try to draw a perpendicular line going through this surface. Okay, so both direction can be the direction of this dA. Maybe you can define a dA to be like this or the other way around. Okay, but after you define one of the direction, then you need to use it all the way. Don't try to use it sometimes pointing to the right, sometimes pointing to the left. Then you make mistakes. You have an additional negative sign, something like that. So yeah, so for some of the case, you can either define for either direction. But after determining the direction, then you need to use it all the way. Okay, and so here we have the area vector with this direction to be perpendicular to the element, and the magnitude is equal to the area. And so we can further define the electric flux d phi. Okay, d phi is the electric flux. Okay, so the electric flux through a patch, or you can consider through a patch element. Okay, through a patch element with area vector dA is given by a dot product. Okay, so suppose we have an element which is a part of a surface, and then for this element we can actually calculate the electric flux of this element. Okay, suppose the E is pointing to a certain direction, and then we have another dA. Okay, so in such a way, we can have this d phi to be the dot product or the inner product. It depends on how you call it. Okay, so this is just a dot product E dot dA. Okay, so here we have a E, we have a dA, so we can have the dot product, and for the dot product, it turns out to be a scalar. Okay, so for the scalar, we only consider its value. Okay, there's only a scalar. It's just a value. No direction for it. So so this d phi or delta phi. Okay, no, it doesn't matter. So it is just the magnitude of the E. Okay, so we have the E here, and then the dA vector. The magnitude of the dA vector is actually the area of this patch. Okay, of course you can consider like it is actually d phi to be E times dA. Okay, yeah, it doesn't really matter. You call it dA or delta A, d phi or delta phi. It is actually the same thing. And then cosine of theta. Theta is the angle between the E and dA. Okay, so here you can see this is the theta. Okay, so E dot dA is nothing but E. Okay, so this is E, this is dA times cosine of theta. Okay, so you have to remember how to calculate the dot product. And I suppose you should have learned it in high school physics. Okay, so this is the case if E and dA have an acute angle between them. Okay, so in that case, cosine of theta will be a positive value. Okay, so here if theta is less than 90 degree and larger than 0 degree, then cosine of theta will be a positive value. Okay, so for this case, and in this case, yeah, and actually if theta is 90 degree, then cosine of theta will be 0, and if theta is less than 180 or and larger than 90 degree, then cosine of theta will be a negative value. Okay, something like that. So in that case, d phi can be a positive or negative value, depends on the direction of the E and the dA. Okay, so here comes the overall direction of the electric flux. So here it says now we can find the total flux by integrating the dot product over the full surface. By integrating the dot product. So here we have the total flux. By integrating the dot product over the full surface. So just now I mentioned that we could have a large surface, can be open or closed, and then we try to cut this surface into many small elements. So for each element we can really calculate this d phi, and to say we need to integrate all this dot product means we add all this d phi together. Okay, so which means we try to integrating the d phi, Okay, so according to calculus class, the integration is actually like to add all these E dot add all this E dot dA together. Okay, adding over all the element on the surface. So It's just like the Riemann sum. Okay, but yeah, we actually don't need to go that deep, but actually you can just consider this integration is nothing but to add all of them together. And actually in this course, if you need to calculate something by your hands, then for most of the cases, they will become quite uniform. Maybe they only have one values or two values. So this kind of add is just like a multiplication. So it doesn't necessary to be quite complicated. Okay, so in such a way we define this total flux. This total flux for a surface. Okay, so for total flux, this surface is actually an open surface, or it can also be applied to closed surface, but it can be open or closed. But usually we will refer this total flux to an open surface, Okay, so for the net flux we will use it for closed surface, So here is, you can understand it as a surface means an open surface, Okay, so it's given by this phi to be integration of E dot dA. So in the previous page we have a d phi to be this one. So you just put it there. And then for this phi we have the SI unit. Nm square over c. So why is it like this? So if you still remember the SI unit for the SI unit of E, SI unit of E is actually N over C, if you still remember. Okay, if you can't really remember, okay, actually you should remember something like E is actually the F over the Q. Okay, so this is the definition of the E field. So this is a Newton. Okay, force, the SI unit for the force should be Newton. Again, for this one, the SI unit for the charge is Coulomb. Okay, so N over C for this one. And then area, the SI unit for area should be meter square. Okay, so altogether N times meter square and then over Coulomb. Okay, so this is the SI unit for the phi. And then the next one is called the net flux. Okay, net flux. Okay, net means 净，就是平常如果说一间公司它赚钱亏钱的话，就是他会讲一些什么净利润就是可能赚到的钱减去一些成本啊，它就是一个净的概念，就是 so for this case, the flux, okay, maybe some E field are pointing outside, some of them are pointing inward, okay, and then in that case, for the flux pointing outside, it is a positive value. For the flux pointing inside, it is for the E field pointing inside, the flux is a negative value. So they may cancel part of that. Okay, so in that way, we just consider the total flux, actually the net flux. So after adding all the small flux together. Okay, so this is the net flux through a closed surface, for a closed surface, which is used in the Gauss law. Okay, so in this textbook, it uses Gaussian surface all the way. Okay, but actually the Gaussian surface and closed surface actually mean the same thing. Okay, so when you just look at the definition, okay, these two definitions are very, very similar. Okay, so maybe I just erase some of it. Okay, so when you just consider this one and this one, okay, it looks very, very similar. The only different part is here we have a circle. So this circle only means that this integration is for a closed surface. So we draw a circle here, okay, which means it's closed. Okay, for some of the math textbook, it will have a more rigorous notation. Actually, here dA is an area. Okay, it is two-dimensional. It is two-dimensional. So for some of the textbook, it will use two integral sign. It will use two integral sign. But in this textbook, it just use one. Okay, but keep in mind that, okay, so it can be one-dimensional, two-dimensional, even three-dimensional in the textbook. It still use a single integral sign. Okay, but actually maybe when you learn in the calculus in the math class, okay, so the easiest one can be something like integration of f of x dx. Okay, so this is one-dimensional. And then there can be two-dimensional integration, something like f of xy and then dx dy, something like that. Okay, this can be a two-dimensional integration, but this one is a little bit different. Okay, so for that case, it is only integrate over the x-axis and y-axis. But this one, okay, so for this case, it is still on a plane. But for this one, okay, you're integrating dA over the closed surface or an open surface. It can be a curvature, so it is not necessary to be on a plane. Okay, so the case is a little bit more complicated here. Okay, but actually you keep in mind that this is actually called a surface integral. Surface integral. Actually, for both of them, we can call it a surface integral. 就是叫做面积分 surface integral. Okay, later in this course, you will also learn the line integral. Okay, a line integral. In chapter 29, we will talk about the line integral. So for the line integral, it can be something like integration of b dot ds. Okay, so this is a line, but it is a curved line. Okay, 就是沿着一个曲线去积分啊。那跟那个 dx 又不一样 ，dx 的话就是x 轴它是直的，那 ds 的话可以是曲的那个叫做 line integral 还有三维的也有三维的对，在后面再说吧。反正现在为止的话，就是有这个 total flux 跟 net flux So up till now we have defined the total flux and net flux, which are surface integrals. Okay, so for the total flux, it is defined for open surface. Okay, so we don't have a circle here. And then for the net flux, okay, it looks quite similar. The only difference is we have a circle. This circle specified. This is a closed surface integral. This is a closed surface integral. Okay, so when you just look at this symbol, it is quite horrible, but actually you can just consider we try to have the surface, or maybe it can be a closed surface, then as much as we need to calculate its net flux, then we try to separate it into many small elements, just like what we draw on this figure. Okay, so after cutting it into many small elements, each element you can consider as a plane, and all of them has a area vector, and for each element you can really calculate the d phi to be E dot dA at that point. Okay, so in such a way, after getting all the E dot dA for each of the elements, then you can add them together. So this summation, we just write it as a integral. We just write it as an integral. 所以就是符号上它是这样的，但是实际上你可以想象成它就是加总你把它切很细之后，全部乘起来，然后我们再加起来。Okay, so where the integration is carried out over the entire surface. Okay, so note phi is larger than 0 outward, and phi is less than 0 inward. Okay, what does it mean? Okay, so just now I mentioned that the dA can have two direction for an element. But for the closed surface, we need to define the dA to be pointing outside. OK， 就是这个 dA 的方向，如果对于一个封闭曲面的话，它一定要指向外面。就是比如说像这个应该像一个心形吧，啊，是像个心形。那每一个曲面你画一个垂直线，应该说每一个小的面，你画一个垂直线，你可以定义它往外往内。那封闭曲面的话，一定要往外啊，一定要往外。Okay. So in such a way, if we let's say for this point, okay, we need to define dA to be pointing outside, okay, pointing outside, and if this E field is perpendicular to it, okay, so let's say this E field, okay, you can see many blue arrows pointing to the right side, okay, so we assume this E field at this point is pointing to the right side and is perpendicular to it. Then for this patch, for this element, d phi will be E dot dA, and in this case E and dA are perpendicular to each other, which will be 0. And for example, for this point, we assume that dA may be pointing to this side, and then the E field pointing to the right side. So there is an angle theta between them to be, okay, so it has a theta, okay, to be less than 90 degrees. So in such a way, d phi will be a positive value. And maybe for this point, okay, so dA may be pointing to this side, and then E field is pointing to that side, okay. So this theta is larger than 90 degree and smaller than 180 degree. So in that case, this d phi is negative for this case, and then d phi is positive for that case, and then d phi can be 0 for that case. So here, okay, so here, this is a big phi, so which means that you need to add all these small d phi together. Okay, if finally the sum is positive, so we will say the flux, the electric flux is going outward. Okay, and then if phi is negative, and then we will say the flux is going inward. Okay, 所以这个它中文叫做通量嘛。所以就是看它通往外面还是通往里面。通往外面的话，它就是有一个正值；通往里面的话，它就是有负值。Okay, so this is the definition of the electric flux. So far, any questions? Okay, no, let's move on. Yeah, okay. Also, I think I already mentioned this, but actually I can draw another figure to elaborate a little bit more. So that, okay, let's assume we have a positive charge. Let's assume we have a positive charge. So, and here we try to assume this is the Gaussian surface. This is the Gaussian surface, and according to what you have learned in chapter 22, you know it will generate E field, okay, pointing outside, okay, because the charge is positive. Okay, so in such a way, for every point on the Gaussian surface, so let's say for this point, dA is pointing outside, dA is pointing outside perpendicular to the surface, dA is pointing outside perpendicular to the surface, something like that. So in such a way, all the E dot dA are positive, okay? So d phi to be E dot dA for all these 4 cases, or even for other direction, I just draw 4 of them. But actually, for this closed surface, it is actually 3D. Okay, so I have no no way to draw all of them. So I just draw 4 of them for demonstration. And you can clearly see that all the E dot dA are positive. So in this way, all of them are positive. All of them are positive. So all the positive value, you add them together, it will still be positive. And similarly, if we have negative charge, and here we have this Gaussian surface, okay? So as I mentioned, this Gaussian surface doesn't necessarily to be a practical surface. It can just be an imaginary surface. 是可以只是在想象中出现。Okay, so in that case, this negative charge will generate E field, okay, pointing towards the charge. Pointing towards the charge. Okay, so in such a way, we can also have dA no matter what, okay, dA always pointing outside of the cold surface, okay, dA always pointing outside to the surface, dA, okay, something like that. Okay, so similarly, when you calculate d phi equals E dot dA, okay, E and dA are always positive, but here we have a theta to be 180 degree. Cosine of 180 degree is -1. So this one is always negative. This one is always negative. So when you add all the negative values together, the sum will be a negative value. Okay. So it is to say phi is positive for outward and then phi for negative for inward. And you can somehow see that, okay, so these E field are something like flowing outside. Okay, this is like a source, okay, to generate the E field, okay, and then going outside. And then here, this negative charge is like a sink, or the E field are pointing towards it, okay. Okay, so here we have a sample problem. Okay, so here it says a Gaussian surface in the form of a cylinder of radius r immersed in a uniform electric field. Okay, 这里有一个电场，均匀电场指向右面然后有一个Gaussian surface 是一个圆柱形的，然后它跟这个圆柱形的轴跟这个 E field 是平行的 ，OK。And then with the cylinder S is parallel to the field, okay. What is flux phi of the electric field through this closed surface? Through this closed surface. Okay. Okay. So it talks about the axis of the cylinder, axis of a cylinder. 那这个是一个正的圆柱形，正的圆柱形的话就是两边就是正圆形，然后对准嘛。那所以的话，它的轴的话就是把两个圆心连起来，这个就是叫做那个 axis of the cylinder axis of the cylinder。那 axis of the cylinder 就是跟 E field 平行的，它也没有所谓的方向，是吧？反正它就是一个轴，你爱它往左往右都无所谓。就通常叫做 Z 吧，通常叫做 Z。Okay, so we try to calculate the flux for this cylinder. Okay, this cylinder is actually a closed surface. So here we try to calculate phi to be the closed surface integral of E dot dA. Closed surface integral of E dot dA. So here we can separate this cylinder into 3 parts. The part A is the left circle, and the B is the side, and then the C is the right circle. Okay, so for the integration, we can actually separate into 3 parts and then add them together. For part A, E dot dA, and then plus the sorry, this is not closed anymore. Okay, so for A, it is just a circle, so I don't draw a circle here. So B and then E dot dA, and then plus C and then E dot dA. Okay, so we just try to separate this circle into part A, part B, and part C. Okay, so we write it as A, B, C here. Okay, so for integration of A, E dot dA, okay. Okay, so in this case, as much as dA is perpendicular to the circle and then pointing outside of this cylinder. Okay, so dA is pointing to the left side, and then as we mentioned, this E field, this uniform E field is pointing to the right side. Okay, so in this way, this theta is 180 degree. So this integration will be E times dA times cosine of 180 degree. Okay, so this one is -1, so finally it turns out to be, okay, maybe this is A, this is A. And then finally it becomes negative EA. Okay, so you may ask, oh, where is the D? Okay, so my point is actually for this case, E is a constant. E is a constant over this surface. Okay, so for this point it is something like this. For another point it is also dA and then E field, something like this. So it is like integrating a constant. Integrating a constant, it turns out to be a multiplication. It is something like you try to integrate 3 dx from 0 to 4. Okay, so it will be just like 3 you putting out and then dx from 0 to 4. Okay, so this one is nothing but a 4, so it turns out to be 3 times 4, something like that. Okay, so for this case, you need to check E dot dA over the whole surface. So it turns out to be the E field or the uniform E field multiplied by the total area of this surface. Okay, we just make it like E. Don't try to make it like pi r squared, although you know that. But here we just assume that the A is the area of the circle. Area of the circle. Okay, it is already okay for now. Okay, and then for part B, or maybe we go to part C first. Part C is easier. Part C is this circle. Okay, so similar to part A, okay, we have dA pointing to the right side. Okay, pointing outside of this cylinder. Okay, so and then also perpendicular to this circle. So this dA points to the right side, and then E field also points to the right side as it is uniform over the whole case. So in this case, E dot dA for part C will be nothing but E times A, okay, without a negative sign, because for this one, dA and E points to opposite direction, but here E and dA point to the same direction. Cosine of 0 degree is 1, so here we only have an EA. And then for the part B, we need some discussion. So in this case, for example, for this point, E field pointing to the right side, and then the dA is perpendicular to the surface. So for this point is pointing upward. Okay, so here this theta is 90 degree. Okay, so for other points, okay, although dA are actually pointing to the different direction. For example, if you consider a point here, dA is pointing downward, and the E field is still pointing to the right side. Okay, so in such a way, this theta is also 90 degree. Even for this point, okay, this dA will be pointing towards us, okay, out of the page, 就是指向我们的方向，就是垂直那个纸面指向我们的方向。然后这个and then the E is still pointing to the right side. So even for this case, this theta is 90 degree. Okay, so over the side of this cylinder, okay, we can always get E dot dA is 0. Okay, so in such a way, we add all the 0 together. So this surface integral turns out to be 0. Okay, so we already get this one, this one, this one, so the remaining stuff is to add them together. So it is actually negative EA plus 0 plus EA. Okay, so it turns out to be a 0. Turns out to be a 0. So this is nothing but a simple sample problem to let you familiar with this notation. Okay, and then as much as this is a uniform function inside the integration, it turns out to be a multiplication. So don't consider this, okay, this is very complicated. Actually, it uses a very complicated mathematical notation so that it makes you have a simple calculation. Usually we only do multiplication， 就是这个积分呢，就是通常都是在物理里面，通常都是算一些很均匀的情况。那算均匀的情况的话，它积分就会变成一个乘法。但如果你去上数学课的话，它就会出一些奇怪的函数给你去积分了，你就可能要积一阵子嘛。但是在这里的话，通常会比较简单的。Okay, so let's have a 15 minutes break and then we continue.